Hello, I will be going over photoelectron spectroscopy or PES. So I'd assume before watching this video, you have basic knowledge of the quantum mechanical orbit or atomic model, so spfd, orbitals, and how they're ordered, and Hund's rule, and stuff like that. So essentially, what photoelectron spectroscopy is it's used to determine the relative energies of electrons in atoms and uses a graph which we'll see later with peaks at different binding energies to represent subshells and the amount of electrons in those respective subshells, as well as their binding energy, in this case, the electrons binding energy. Which means how much energy is required to keep an electron in a specific shell. So normally, the closer you get to zero in binding energy, the easier it is to break the electron away from its subshell. So you'll see a graph that looks something like this when you get a question on PES. So you have two axes, I guess you could say. You have the number of electrons in the y-axis, and you have the binding energy on the x-axis. And then you have each peak, which represents every subshell and how many electrons there are. So the key number that you need to, or the key numbers you need to know are the number of electrons of the y-axis, because that will tell you how many electrons are in each subshell. And so if we take a look at this, we have, so each one of these peaks represents a subshell. So this would be the 1s, or the orbital. This would be 2s. This would be 3s. This would be, or sorry, not 3s, 2p. This would be 3s. And this would be 3p. And 50 seconds. This would be, this one would be 4s. And this one will be 3d. So that follows just Hund's rule, which is down here, how it's formatted. So 1s, 2s, 2p, 3s, 3p, 4s, 3d. And so if we look at where the peak lines up with the number of electrons, we could see that this first peak here at 433 megajoules a mole has 2 electrons. So it would be 1s2. And then we can see in the second peak, it's 2s. There's there's 2 electrons, so it's 2s2. And then on the third peak, it goes all the way up to 6 electrons. So this is filled up to the max. And we know that because otherwise this peak here would overfill to here if there was 7 electrons, for example. But we know that it's filled up to the max because we know that 2s orbital can hold 6 electrons max. So that is going to be 2p6. And then we have the fourth one, it's 3s2. The fifth one, 3p6, again, because it reaches 6 number of electrons on the y-axis. And 4s, so see how it's kind of half of the first peak. That means there's only 1 electron. So 4s1, and again 3d2, 3d2, because there's 2 electrons there. And if we combine this to form an electron configuration, we get 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d2. And if we add all these up, we get the final count, which equates to scandium. So yeah, it's essentially how you can figure out the element from a PES graph, where you're given the binding energy on the x-axis and the number of electrons in the y-axis. So here's an example you can try again. Um, all you have to know, the main number, or the main, I guess, axis would be the number of electrons, and then you just see where the peaks end up. So give that one a try. Okay, so hopefully you had enough time to at least get the electron configuration. You don't have to get the element, but I will go over what it'll be. So we have, again, 1s2, because it goes to the 2, goes up to 2, 2s2, 2p6, because it goes up to 6, 3s2, 3p6 again, because it goes up to 6, and 4s2. And there's nothing on the right side, which means that that's all we've got. So it's 1s2, 2s2, 2p6, 3s, whoops, 3s2, 3p6, and finally 4s2. And that equates to calcium. So I hope this short video has helped a little bit in understanding PES graphs and what they're used for. See you.